In today's video, I'd like to discuss coordinate optimization. Now, coordinate optimization was something that we did in single variable calculus. So let's say I had a parabola of some sort, right? I could have a parabola or I could have a line of some sort, and I would want to find like a shortest distance, right? So I'd have a parabola or something or a function, and then I'd have a point, and I would say where on our parabola is closest to this point. So it could be there, it could be there. It's likely to be there though. But anyways, that is how coordinate optimization works in single variables. Now, obviously, we can expand this to multivariable. The two-variate case is obviously the most easy to visualize, simplest to visualize. But we can use the three-variate case as well. So we're just going to do a quick example to show how we can deal with this with the Lagrange multiplier method that we learned earlier. So let's discuss this with a quick example. We'll get that right out of the way. So I would like us to find the point closest to and farthest from the point xyz equals 3, 1, negative 1 from a sphere at the origin whose equation is x squared plus y squared plus c squared equals 4. So this is a sphere. So if I have my xyz plane, I have some sort of, will look like an elliptical base there. And then we go up kind of our northern hemisphere and then our southern hemisphere. And we want to determine that this has a radius of 2 and it's centered at the origin. And we write this as our constraint equation because this constrains where our point can be. It says it needs to be on the surface of the sphere. So we need to have that as our constraint. So that will be g of x, y, and z. And g, for the Lagrange method, we have g of x, y, and z equal to some k. And here it looks like we're equal to 4. Now we also have what we actually want to find, and that is the minimum distance between our point and the sphere. So we'll say that the distance squared is equal to x minus 3 quantity squared plus y minus 1 quantity squared plus c plus 1 quantity squared. And that will be equal to f of x, y, and z. So now we have our two equations. So we know g equals 4 from what we determined here. We also know that nabla f equals lambda, some Lagrange multiplier, times nabla g. So what we can do now is we can find the gradients of both of these functions, which is pretty easy, and we get a vector equation that looks like this. We differentiate each part, use the chain rule as you like. You get 2 times x minus 3, 2 times y minus 1, 2 times z plus 1 equals lambda times 2x, 2y, and 2z. Now what we can do is we can use each of these equations to solve for x in terms of lambda, or x, y, and z in terms of lambda, and then we can plug that into our distance equation, or into our sphere equation, which will make our lives easier. So we get x equals 3 over 1 minus lambda, y equals 1 over 1 minus lambda, and z equals negative 1 over 1 minus lambda. Thus, we get, when we plug back into our equation, we get 1 minus lambda squared equals 11 over 4. So here, as you can see, we're plugging this into our equation for the sphere. And then we can solve that for lambda. It's fairly easy quadratic. We get lambda equals 1 plus or minus the square root of 11 over 2. So now we know that our coordinate pairs x, y, and z are going to be, our coordinates x, y, and z are going to be 6 over square root 11, 2 over square root 11, and negative 2 over square root 11. That's for one case, and then you can solve for the other case easily by taking the negative case of the square root. So that is coordinate optimization with the Lagrange multiplier method. In the next video, we want to just briefly talk about the case where we have two unknown constraints, or we have two constraints, and we call the other constraint mu. So we've got lambda and mu, Greek letter for L and Greek letter for M, I think. And then after that, we are ready to move on to multivariable integration, which is really going to be fun, but it is a tough topic. So we'll get into that later. Thanks for watching. We'll see you next time. Bye.